Download this code from codegive.com, link in the description below. The 0/1 knapsack problem, a deep dive with dynamic programming. The 0/1 knapsack problem is a classic optimization problem with a surprising range of real-world applications, from resource allocation to investment management. It belongs to the class of NP-hard problems, meaning there's no known polynomial time algorithm to solve it for all cases. However, dynamic programming provides an efficient solution for reasonably sized inputs. This tutorial will comprehensively cover the 0/1 knapsack problem, focusing on the dynamic programming approach. We'll break down the problem definition, explore the dynamic programming logic, provide a step-by-step implementation with detailed code explanation, discuss optimizations, and touch upon some variations. 1. Problem definition. Imagine you're a hiker preparing for a backpacking trip. You have a knapsack with a limited weight capacity, W. You're presented with a collection of items, each with its own weight, W_I, and value, V_I. Your goal is to choose a subset of these items to place in your knapsack such that the total weight of the chosen items does not exceed the knapsack's capacity W. The total value of the chosen items is maximized. The 0/1 in the name indicates a crucial constraint: you can either take an item completely, 1, or leave it behind completely, 0. You cannot take fractions of items. Formal definition Given n items. Wi equals weight of the ith item, I equals 0 to n1. Vi equals value of the ith item, I equals 0 to n1. W equals maximum weight capacity of the knapsack. Objective: maximize sigma vi xi, where xi is either 0 or 1, representing whether to include item I or not. Subject to sigma wi xi equals w. Example *. Let's say we have the following items. Item weight, W, value, V. Dash 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 dash. 116. 2210. 3312. And the knapsack's capacity, W equals 5. The optimal solution would be to take items 1 and 3, with a total weight of 1 plus 3 equals 4, equals 5, and a total value of 6 plus 12 equals 18. 2. Why dynamic programming? While it might seem tempting to use a greedy approach, example always pick the item with the highest value per unit weight, greedy algorithms don't guarantee the optimal solution for the 0/1 knapsack problem. A greedy approach might lead to filling up the knapsack with less valuable items, leaving no space for more valuable, heavier items. Dynamic programming, on the other hand, systematically explores all possible combinations of items by breaking down the problem into smaller, overlapping subproblems. It builds a table, or memoization structure, to store the solutions to these subproblems, avoiding redundant computations and ensuring that we arrive at the optimal solution. 3. Dynamic programming approach, building the table. The core idea of the dynamic programming approach is to create a table dpiw where *I represents the number of items considered so far, from 0 to n. *W represents the current knapsack capacity, from 0 to W. *dpiw stores the maximum value that can be obtained using the first I items with a knapsack capacity of W. The recurrence relation *. The key to dynamic programming is defining the recurrence relation that connects the solution of a larger problem to the solutions of smaller subproblems. For the 0/1 knapsack, we have two choices for each item I. Asterisk include item I asterisk if the weight of the current item WI1, remember, indexing starts from 0, is less than or equal to the current knapsack capacity W, then we can include it. The value we get is VI1, the value of the current item, plus the maximum value we can get using the remaining capacity, W, WI1, with the previous I1 items. This translates to dPIW equals VI1 plus dPI1W, WI1. Asterisk exclude item I asterisk if we don't include the current item, the maximum value we can get is simply the maximum value we can get using the previous I1 items with the same knapsack capacity W. This translates to dPIW equals dPI1W. We choose the option that yields the maximum value. dPIW equals max, dPI1W, VI1 plus dPI1W, WI1, if WI1 equals W. dPIW equals dPI1W if WI1W. Base cases asterisk. Asterisk dP0W equals 0 for all W, if we have no items, the maximum value is 0, regardless of the knapsack capacity. Asterisk dPI0 equals 0 for all I, if the knapsack capacity is 0, the maximum value is 0, regardless of the number of items. 4. Step-by-step construction of the DP table. Let's illustrate how the DP table is built using the example from earlier. Asterisk n equals 3, number of items. Asterisk W equals 5, knapsack capacity. Asterisk W equals 1, 2, 3, weights of items. Asterisk V equals 6, 10, 12, values of items. We initialize a, n plus 1, x, w plus 1, table filled with zeros. Now, we fill the table row by row, starting from row 1 and column 1, using the recurrence relation. Asterisk I equals 1, item 1, weight 1, value 6. Asterisk dP10 equals 0, base case. Asterisk dP11 equals max, dP01, V0 plus dP01 W0, equals max, 0, 6 plus dP00, equals max, 0, 6, equals 6, we can include item 1. Asterisk dP12 equals max, dP02, V0 plus dP02 W0, equals max, 0, 6 plus dP01, equals max, 0, 6, equals 6. Asterisk dP13 equals max, dP03, V0 plus dP03 W0, equals max, 0, 6 plus dP02, equals max, 0, 6, equals 6. Asterisk dP14 equals max, dP04, V0 plus dP04 W0, equals max, 0, 6 plus dP03, equals max, 0, 6, equals 6. Asterisk dP15 equals max, dP05, V0 plus dP05 W0, equals max, 0, 6 plus dP04, equals max, 0, 6, equals 6. Asterisk I equals 2, item 2, weight 2, value 10. Asterisk dP20 equals 0, base case. Asterisk dP21 equals dP11 equals 6, item 2 is too heavy for capacity 1. Asterisk dP22 equals max, dP12, V1 plus dP12 W1, equals max, 6, 10 plus dP10, equals max, 6, 10, equals 10, we can include item 2. Asterisk dp23 equals max, dp13, v1 plus dp13 w1, equals max, 6, 10 plus dp11, equals max, 6, 10 plus 6, equals 16. Asterisk dp24 equals max, dp14, v1 plus dp14 w1, equals max, 6, 10 plus dp12, equals max, 6, 10 plus 6, equals 16. Asterisk dp25 equals max, dp15, v1 plus dp15 w1, equals max, 6, 10 plus dp13, equals max, 6, 10 plus 6, equals 16. Asterisk I equals 3, item 3, weight 3, value 12. Asterisk dp30 equals 0, base case. Asterisk dp31 equals dp21 equals 6, item 3 is too heavy. Asterisk dp32 equals dp22 equals 10, item 3 is too heavy. Asterisk dp33 equals max, dp23, v2 plus dp23 w2, equals max, 16, 12 plus dp20, equals max, 16, 12, equals 16. Asterisk dp34 equals max, dp24, v2 plus dp24 w2, equals max, 16, 12 plus dp21, equals max, 16, 12 plus 6, equals 18, we can include item 3. Asterisk dp35 equals max, dp25, v2 plus dp25 w2, equals max, 16, 12 plus dp22, equals max, 16, 12 plus 10, equals 22, typo fix here in the explanation and subsequent table. The final answer, the maximum value we can obtain, is stored in dpnw, which is dp35 equals 22. Asterisk incorrect. The optimal value as calculated in the previous section should be 18 star. Let's correct the calculations for I equals 3. Specifically, the value dp35 should be asterisk dp35 equals max, dp25, v2 plus dp25 w2, equals max, 16, 12 plus dp22, equals max, 16, 12 plus 10, equals max, 16, 22, equals 22. This is still incorrect if the items we choose are 1 and 3. Let's re-examine I equals 2 values. Asterisk dp20 equals 0. Asterisk dp21 equals dp11 equals 6. Asterisk dp22 equals max, dp12, v1 plus dp12 w1, equals max, 6, 10 plus dp10, equals max, 6, 10, equals 10. Asterisk dp23 equals max, dp13, v1 plus dp13 w1, equals max, 6, 10 plus dp11, equals max, 6, 10 plus 6, equals 16. Asterisk dp24 equals max, dp14, v1 plus dp14 w1, equals max, 6, 10 plus dp12, equals max, 6, 10 plus 6, equals 16. Asterisk dp25 equals max, dp15, v1 plus dp15 w1, equals max, 6, 10 plus dp13, equals max, 6, 10 plus 6, equals 16. Recalculating the values for I equals 3. Asterisk dp30 equals 0. Asterisk dp31 equals dp21 equals 6. Asterisk dp32 equals dp22 equals 10. Asterisk dp33 equals max, dp23, v2 plus dp23 w2, equals max, 16, 12 plus dp20, equals max, 16, 12 plus 0, equals 16. Asterisk dp34 equals max, dp24, v2 plus dp24 w2, equals max, 16, 12 plus dp21, equals max, 16, 12 plus 6, equals max, 16, 18, equals 18. Asterisk dp35 equals max, dp25, v2 plus dp25 w2, equals max, 16, 12 plus dp22, equals max, 16, 12 plus 10, equals max, 16, 22, equals 22 is still incorrect. The items picked for weight 5 should be items 2, weight 2, value 10, and 3, weight 3, value 12, with a total value of 22. My apologies for the prior confusion. The optimal solution using items 1 and 3 totals only weight 4, so this is incorrect. The corrected table asterisk. Therefore, the maximum value we can obtain is dp35 equals 22. 5. Code implementation, Python. Code explanation asterisk. 1 knapsack underscore 01, w, w, v, n, function asterisk. Asterisk takes the knapsack capacity w, the weights list w, the values list v, and the number of items n as input. Asterisk creates a 2D array dp of size, n plus 1, x, w plus 1, initialized with zeros. This represents our dynamic programming table. 2 outer loop, iterating through items for I in range, n plus 1. Asterisk iterates from 0 to n, inclusive, where I represents the number of items considered so far. The I equals 0 case represents the base case of having no items. 3 inner loop, iterating through capacities for weight in range, w plus 1. Asterisk iterates from 0 to w, inclusive, where weight represents the current knapsack capacity. The weight equals 0 case represents the base case of having 0 capacity. 4 base cases asterisk if I equals 0 or weight equals 0. Asterisk if either the number of items is 0 or the knapsack capacity is 0, the maximum value is 0. We set dpi weight equals 0. 5 decision, include or exclude item if wi1 equals weight. Asterisk if the weight of the current item wi1, remember, indexing is 0 based, is less than or equal to the current knapsack capacity weight, then we have 2 choices. Asterisk include the item asterisk vi1 plus dpi1 weight wi1. This adds the value of the current item vi1 to the maximum value we can obtain using the remaining capacity weight, wi1 with the previous i1 items. Asterisk exclude the item asterisk dpi1 weight. This represents the maximum value we can obtain using the previous i1 items with the same knapsack capacity weight. Asterisk we take the maximum of these 2 options, dpi weight equals max, vi1 plus dpi1 weight wi1, dpi1 weight. 6 item 2 heavy asterisk else. Asterisk if the weight of the current item wi1 is greater than the current knapsack capacity weight, we cannot include the item. Therefore, the maximum value is simply the maximum value we can obtain using the previous i1 items with the same knapsack capacity weight, dpi weight equals dpi1 weight. 7 return the result asterisk return dp and w. Asterisk after filling the entire dp table, the maximum value that can be obtained using all n items with a knapsack capacity of w is stored in dp and w. 6. Optimizations. Asterisk space optimization, reducing to 1D array. Notice that in the inner loop, we only need the values from the previous row, I1. Therefore, we can optimize the space complexity by using only a 1D array dpw plus 1 and iterating in reverse order for the inner loop. This prevents overwriting values that will be needed in subsequent calculations. 7. Recovering the items selected, backtracking. The above code provides the maximum value. If you need to know which items were selected to achieve that maximum value, you can perform a backtracking step after the DP table is constructed. Explanation of backtracking asterisk. 1. Start at dpnw. 2. If dpiw equals dpi1w, it means item I was not included, so move to dpi1w. 3. If dpiw equals dpi1w, it means item I was included. Add item I to the selected _items list, and move to dpi1w, wi1, reduce the capacity by the weight of the item we included. 4. Repeat steps 2 and 3 until you reach I equals 0. 8. Complexity analysis. Asterisk time complexity asterisk O, n backslash asterisk W, where n is the number of items and W is the knapsack capacity. We iterate through the DP table, which has dimensions, n plus 1, x, W plus 1. Asterisk space complexity asterisk. Asterisk O, n backslash asterisk W, for the standard DP solution. Asterisk O, W, for the space optimized solution. Important note asterisk the time complexity is pseudo-polynomial. It depends on the value of W, not just the size of the input. If W is very large, example on the order of 2n, the algorithm can become inefficient. 9. Variations and extensions. Asterisk unbounded knapsack. Knapsack with repetition. You can take multiple copies of the same item. The recurrence relation changes. Instead of dpi1w, wi1, you'd use dpiw, wi1 because you can potentially take more of item I. Asterisk fractional knapsack. Greedy approach. You can take fractions of items. A greedy approach, sort by value to weight ratio, works optimally for this variation. Asterisk multidimensional knapsack. Asterisk items have multiple constraints, example weight and volume. You'd need a DP table with more dimensions to track the different constraints. Asterisk constrained knapsack. Asterisk additional constraints, example maximum number of items that can be included. 10. When to use 0/1 knapsack. The 0/1 knapsack is suitable when asterisk you need to select a subset of items from a larger set. Asterisk each item has a value and a weight. Asterisk there's a constraint on the total weight, or resource usage. Asterisk you must take an item completely or not at all, no fractions. Asterisk the number of items and the capacity W are within a manageable range for dynamic programming. In summary, the 0/1 knapsack problem is a powerful tool for solving optimization problems involving resource constraints and item selection. Dynamic programming provides an efficient way to find the optimal solution, especially when greedy approaches fail. By understanding the recurrence relation and the table building process, you can adapt this algorithm to solve a variety of similar problems. Remember to consider the space optimization to improve efficiency when memory is a concern, and to implement backtracking if you need to identify the specific items included in the optimal solution.